Center of mass. We shall first see what the center of mass of a system of particles is and then discuss its significance. For simplicity, we shall start with a two-particle system. We shall take the line joining the two particles to be the x-axis. Figure 7.7. Let the distances of the two particles be x1 and x2 respectively from some origin O. Let m1 and m2 be respectively the masses of the particles. The center of mass of the system is that point C, which is at the distance x from O, where x is given by x equals m1 x1 plus m2 x2 divided by m1 plus m2. In equation 7.1, x can be regarded as the mass weighted mean of x1 and x2. If the two particles have the same mass as m1 equals m2 equals m, then x equals mx1 plus mx2 by 2m, which equals x1 plus x2 by 2. Thus, for two particles of equal mass, the center of mass lie exactly midway between them. If we have n particles of mass m1, m2 till mn respectively along a straight line taken as the x-axis, then by definition the position of the center of mass of the system of particles is given by x equals m1 x1 plus m2 x2 plus till mn xn divided by m1 plus m2 plus till mn, which equals summation of mi xi where I runs from 1 to n divided by summation of mi where I runs from 1 to n, which equals summation mi xi by summation mi, where x1, x2 till xn are the distances of the particles from the origin. X is also measured from the same origin. The symbol summation, the Greek letter sigma, denotes summation. In this case, over n particles, the summation mi equals m is the total mass of the system. Suppose that we have three particles not lying in straight line. We may define x and y axis in a plane in which the particles lie and represent the position of the three particles by coordinates x1 y1, x2 y2 and x3 y3 respectively. Let the masses of the three particles be m1, m2 and m3 respectively. The center of mass C of the system of the three particles is defined and located by the coordinates x, y given by x equals m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3, y equals m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. For the particles of equal masses m equals m1 equals m2 equals m3, x equals m into x1 plus x2 plus x3 divided by 3m, which equals x1 plus x2 plus x3 divided by 3. Y equals m into y1 plus y2 plus y3 divided by 3m, which equals y1 plus y2 plus y3 by 3. Thus, for three particles of equal mass, the center of mass coincides with the centroid of the triangle formed by the particles. Results of equation 7.3a and 7.3b are generalized easily to a system of n particles, not necessarily lying in a plane but distributed in space. The center of mass of such a system is at x, y, z, where x equals summation mi xi divided by m, y equals summation mi yi divided by m, and z equals summation mi zi divided by m. Here, m equals summation mi is the total mass of the system. The index I runs from 1 to n. Mi is the mass of the ith particle and the position of the ith particle is given by xi, yi, zi. Equations 7.4a, b and c can be combined into one equation using the notation of position vector. Let Ri be the position vector of the ith particle and capital R be the position vector of the center of mass. Ri equals xi into I cap plus yi j cap plus zi k cap, and capital R equals xi cap plus yj cap plus zk cap. Then R equals summation mi ri divided by m. The sum on the right hand side is a vector sum. Note that economy of expressions we achieve by use of vectors. If the origin of the frame of reference, the coordinate system, is chosen to be the center of mass, then summation MIRI equals 0 for a given system of particles. A rigid body, such as a meter stick or a flywheel, is a system of closely packed particles. Equation 7.4 A, B, and C and D are therefore applicable to the rigid body. The number of particles, that may be atoms or molecules, in such a body is so large that it is impossible to carry out the summations over individual particle in these equations. Since the spacing of particles is small, we can treat the body as a continuous distribution of mass. We subdivide the body into n small elements of mass delta m1, delta m2 till delta mn. The ith element delta mi is taken to be located about the point xi, yi, zi. The coordinates of the center of mass are then approximately given by x equals summation delta mi xi by summation delta mi, y equals summation delta mi yi by summation delta mi, z equals summation delta mi zi by summation delta mi. As we make n bigger and bigger and each delta mi smaller and smaller, then these expressions become exact. In that case, we denote the sums over I by integrals. Thus, summation delta mi leads to integral dm, which equals m. Summation delta mi xi leads to summation x dm, summation delta mi yi leads to summation y dm, and summation delta mi zi leads to summation z dm. Here, m is the total mass of the body. The coordinates of the center of mass are now x equals 1 by m into integral x dm, y equals 1 by m into integral y dm, and z equals 1 by m integral z dm. The vector expression equivalent to these three scalar expressions are r equals 1 by m integral r dm. If we choose the center of mass as the origin of our coordinate system, r equals 0. That is, integral r dm equals 0, or integral x dm equals integral y dm equals integral z dm, which equals 0. Often we have to calculate the center of mass of homologous bodies of regular shapes like rings, discs, sphere, rods, etc. By a homologous body, we mean a body with uniformly distributed mass. By using symmetric consideration, we can easily show that the centers of mass of these bodies lie at their geometric centers. Figure 7.8, determining the center of mass of a thin rod. Let us consider a thin rod whose width and breadth in case of cross-section of the rod is rectangular, or radius in case of cross-section of the rod is cylindrical, is much smaller than its length. Taking the origin to be at geometric center of the rod and x-axis to be along the length of the rod, we can say that on account of reflection symmetry, for every element dm of the rod at x, there is an element of same mass dm located at minus x. The net contribution of every such pair to the integral, and hence the integral x dm itself is 0. From equation 7.6, the point for which the integral itself is 0 is the center of mass. Thus, the center of mass of a homogeneous thin rod coincides with its geometric center. This can be understood on the basis of reflection symmetry. The same symmetry argument will apply to homogeneous rings, disc, sphere, or even thick rods of circular or rectangular cross-section. For all such bodies, you will realize that for every element dm at point x, y, z, one can always take an element of same mass at the point minus x, minus y, minus z. In other words, origin is a point of reflection symmetry for these bodies. As a result, the integrals in all are 0. This means that for all the above bodies, their center of mass coincide with their geometric center.